Hello, and welcome to Train Signal. I'm Don Jones, and this is the Relational Database Concepts lesson in the Database Administration Fundamentals course. In this lesson, we'll talk about some of the foundation concepts for relational databases. Specifically, we'll talk about the relationships between tables, rows, and columns, do a brief overview of something called normalization, briefly cover indexes, and talk about SQL Server's physical storage, pages and physical files. As you've already learned, a relational database consists of one or more tables, and each table is essentially a flat file database in and of itself, much like an Excel spreadsheet or a CSV file. Each table typically stores one type of data, information about a customer, a product, a customer's order, a vendor, and so forth. Tables are organized into columns, which are also called domains, and rows, which represent entities. Each column represents one piece of information, a name, an address, a phone number, and so on, while each row contains all of the pieces of information for just one thing, a customer, a product, a vendor, and so forth. For example, in this diagram, we're seeing two different tables. The top table looks like it contains information about customers. So there are three entities or customers in this particular table. Each column contains one piece of information about those entities, an ID number, which is probably used internally to keep track of them, their name, a phone number, an address, city, and state. The bottom table looks like it contains information about customer orders. There are 4 rows here and 4 columns. One of the columns, customer ID, looks like it's actually referring back to the ID column of the customer table, so that could be used to relate these two tables to each other. In addition, each order has information about the order date, the ship method, and an order ID. Database designers try to reduce redundant data in their database design. That helps to improve the storage of the database. After all, if you eliminate redundant data, you can make the database a little smaller. And it also helps to improve the performance of the database in many different ways. The basic idea behind normalization is that each piece of data in the database should be stored only one time within the database. In other words, you shouldn't have duplicate copies of things floating around in the database. You store something just once. If you need to refer to that same data elsewhere, then you do just that. You refer to the data rather than duplicating it. The process of designing a database in this fashion is called normalization. It's something that we'll talk about in much more detail in later lessons for this course, but for right now, a brief overview will help you sort of understand what the idea is and where this is going. This diagram shows a not normalized database design. If you look in the top table, this is very similar to the diagram that we just looked at. The top table appears to contain customer information. The bottom table appears to contain information about customer orders. The problem is the first column in that bottom table. It is duplicating information. Each customer's name is listed here, but that information has already been listed in the top table, so we're duplicating it. One problem we have is that if one of these customers changes their name, for example, maybe when we entered their name the first time, we typed it incorrectly, and so now we'd like to go back in and spell it correctly. Well, we'd have to go find every single instance of that name and correct them all individually, which is obviously wasted effort. Now we're back to our original database design, where instead of listing the customer name in the bottom table, we're listing a customer ID number. This lets us refer to the original information. So rather than putting Don Jones as the first order in our bottom table, we put ID number 17. That refers us back to customer ID number 17 in the top table. Now, if we need to make a correction to that customer's information, we only have to do it in one place. Typically, these references are made using internal ID numbers that are guaranteed to be unique. So there would never be a reason for us to change that 17 to something else. The 17 doesn't have any internal or intrinsic meaning. It's just a unique number that we came up with to represent that particular customer so that we can refer to that customer whenever we need to. Indexes are a very important part of relational databases. Data within a database table is often stored in whatever order it was added, but we rarely want to actually look it up that way. So an index, much like the index in the back of a book, provides a faster way of looking up specific rows by duplicating key pieces of data and storing them in whatever convenient order we want. An index is not a table. It's sort of a cross-reference to a table. We do have to acknowledge that part of the point of an index is to duplicate data. But this isn't a table, so the desires and the rules of normalization, they don't apply here. We're deliberately duplicating just certain key pieces of information, and even though that is making us take up more space in the database, it's also giving us a performance benefit because it allows us to look things up very quickly in whatever order we design. In this diagram, the top table in blue represents our actual customers table. Again, this is listing each customer in the order in which they're added. So if that ID column is simply incremented each time we add a new customer, then you can see that 17, 18, 19, these customers have been stored in the order in which they were added to the database. We're rarely going to need to look that up. We're probably never going to need to grab the 19th customer that was added. That's just not something you'd care about. We would very frequently want to look these folks up by their name or perhaps by the city that they live in. So the two green elements on the bottom are indexes. The first index lists the customers by their last name, first name, and then provides a pointer back to the entire actual data row. So if we needed to look up Amanda Williams, we could quickly scan to the bottom of this list because we know W is going to be near the bottom. We'd find Amanda, and then the index would point us to her complete data. So now we would be able to access her phone number and her address once we knew her name. Or if we needed to look up someone by their city, we could quickly scan to, say, Littletown, and then get a quick cross-reference to the customer who went with Littletown. Now let's talk about SQL's physical storage and how it manipulates that information. SQL Server stores its data on disk in 8 kilobyte chunks that are called pages. And with some exceptions, all data for a single table row must fit within one page. So if you think about a single customer, their ID number, their name, their phone number, their mailing address, all the information that would appear in one row for that customer has to fit within a single 8 kilobyte page. It is okay to have multiple rows on a single page. So if you have a very small row that only takes up a couple of kilobytes, you might be able to squeeze 3 or 4 rows into a single 8 kilobyte page. Index data is also stored in these 8 kilobyte chunks called pages. When SQL Server reads data from disk, or when it saves changes from memory back to disk, it does so one page at a time, so always in those 8 kilobyte chunks. This plays a very important role in how SQL Server actually works. When SQL Server needs to modify data in the database, it goes to the disk, it finds the 8 kilobyte page that contains the data that will be modified, and reads that page into memory. The changes are then made to the page in memory, but they are not instantly written back out to disk though, because SQL Server knows, hey, there might be more changes coming up, and it'll be faster if I just keep this information in memory. That way I can make a bunch of changes to it, and a little bit later I'll put it back on disk so it's safe. And that safe is a key word, because keeping that information in memory puts the data at risk. If there's a power loss or if the server crashes for some reason, all the information that's in memory but has not been saved back out to disk is lost. Now, SQL Server acknowledges that risk, and it uses a transaction log to keep track of the changes it has made and of which changes have been safely written back to disk. So as SQL Server is making changes in memory, it's just quickly adding a little bit to this transaction log on disk. Now this transaction log model, combined with the page structure, is at the very heart of how SQL Server operates. Here's a schematic at a very high level of how SQL Server works. On the top left, we've got SQL Server's memory, which currently doesn't have anything in it. On the top right, there's the disk drive, where the files are physically stored, and they're considered safer there because if the computer loses power or crashes, whatever's on disk is still there. It's not affected. At the bottom, we have the transaction log, which is a very simple file structure that also lives on disk. So let's say we ask SQL Server to make a change. SQL Server goes to the disk drive, grabs the page that will be affected by that change, and reads it into memory. SQL Server then goes ahead in memory and makes the change, so updating some data, maybe adding some data, even removing data. That same change is quickly added to the transaction log, which remember sits on disk. Now that transaction log is not a database in and of itself. It's really just a log file. It's not quickly searchable, it's not scannable, it's not indexable, it's not a good place to look up data, but it's a good way to keep track of the changes that have been made recently. Now let's continue. Let's say SQL Server decides to do another change. So we ask it to do that. It reads that page into memory, makes whatever change is necessary there, and adds that change to the transaction log as well. Now at some point, SQL is going to run out of memory for loading all these things in, and it'll say to itself, I need to free up some memory because there's going to be more changes coming down eventually, and I've got this one page with this orange change that I haven't really made any changes to that page recently, so let's assume that I'm kind of done with that one for now, and go ahead and write it back out to disk. Okay, so now that's on disk, so I'm going to go to the transaction log and just sort of check it off. That'll remind me if I need to read the transaction log later that that change was made and successfully saved back to disk. So now we'll proceed to, oh no, the software crashed, and everything that was in memory was lost. So that change with the green triangle never existed, but it's okay because it's still down there in the transaction log. Each time SQL Server starts, whether it was from a crash or just because you had a planned maintenance and you rebooted the server, whatever, every time SQL Server starts, it goes into something called auto recovery mode. And it looks in the transaction log to see if there are any transactions which have been made but not saved back to disk, like that one that we just saw when the server crashed. SQL Server then repeats or replays those transactions immediately. So it uses that transaction log to recreate the original change. So a very busy SQL Server can thus take some time to start up after an unexpected shutdown or a failure, because its transaction log is likely to contain a large number of uncommitted transactions that need to be immediately replayed in order to bring the database back up to speed. Now the key here is that the transaction log actually stores the literal query instructions that have been executed. So it's kind of like a script that you would give to an actor of what has been done recently, so that that script can be read and acted out again, if necessary, to recover whatever it was we lost because it hadn't yet been saved back to disk. Now that transaction log continues to get longer and longer and longer as changes are made to the database. Once you know you've got a good backup of those database files, so they're not only safe on disk, but they've been safely saved somewhere else, so you have a backup copy, at that point it's safe to truncate the log, which clears out all of those transactions that you know had been safely written to disk, and because they were safely written to disk, you know they're also in your backup, so you've really got 2 copies of those. That's when it's safe to clear those out. That frees up some space in the transaction log, making that space available for new incoming transactions. So truncating the log is an important periodic maintenance thing that you have to do with SQL Server to keep it humming smoothly along. Now you can also make a backup of the transaction log itself, and that's a very, very fast operation, faster than backing up the entire database. And it's one way to ensure that you actually have that valuable data in case it's needed for recovery. And in a later lesson, we'll be talking about backup strategies and how transaction log backups and database backups can work together to really reduce or largely eliminate any data being at risk. This lesson was sort of a crash course in some relational database concepts. We talked about tables, rows, and columns, briefly overviewed what normalization is all about, talked about the role of indexes, and looked at SQL Server's physical storage and page manipulation.